Let's see about AC characteristics of an op-amp. So under AC characteristics, there are two characteristics are there: frequency response and slew rate. Under frequency response, there are two more characteristics: frequency compensation and stability. So under frequency compensation, there are two more characteristics are there: external frequency compensation and internal frequency compensation. Under external frequency compensation, two more frequency compensation techniques are there: dominant full compensation and pole zero compensation or lag compensation. So next, in the frequency compensation, for an ideal case, if the input is equal to 0, means the output should be equal to 0. So under ideal case, the bandwidth is equal to infinite. If the open loop gain is 90 dB with the AC signal, it should be remain at the higher frequency signal. Example for this is audio signal. But practically, the gain will decreases at the high frequency. For an amplifier with only corner frequency, all the capacitor effects can be represented by the single capacitor, that is capital C. This is an high frequency model for op-amp with single corner frequency, that is peak frequency. This is an amplifier model, and by using that model we are doing the analysis. So the output voltage that is equal to AOL, open loop gain, into differential voltage into minus JXC divided by R0 minus JXC. So this is the basic formulas, that is basic approximations regarding this analysis. So finally we are getting the gain is, overall gain is open loop gain that divided by 1 plus J into F by F1. Here F1 is considered as 1 by 2 pi R0 C. Here F1 is the corner frequency, and magnitude modulus A, that is equal to open loop gain divided by 1 plus root of 1 plus F divided by F1 the whole squared. This is equation number 1, and this is the phase value. Phi equal to tan inverse of F divided by F1. It is equation number 2. So this is the characteristics diagram graph. So in that, three options we can analyze. First option is if the F less than the corner frequency, when that time the gain will be 20 log open loop gain in dB. If F equal to F1 means it is 3 dB. If F greater than F1 means gain will be starts to decreases. So when that time it is minus 20 dB per decade or 6 dB per octave. And this is the phase characteristics. So if F equal to 0, phi equal to 0, F1 equal to F equal to F1 means it is minus 45 degree. If F equal to infinite means it is 90 degree, minus 90 degree. So the transfer function is S domain, means that is equal to AOL into the omega 1 divided by omega 1 plus j omega. So omega is replaced by S. After that, final equation for by considering three corner frequencies, AOL into omega 1, omega 2, omega 3 divided by S plus omega 1 into X plus omega 2 into S plus omega 3. So the approximate open loop gain versus frequency curve will be like this. And stability of the op-amp. This circuit is a op-amp with resistive feedback network. By using that circuit, we are doing the analysis. Closed loop gain for that is capital A divided by 1 plus A beta. A is the open loop voltage gain, beta is the feedback ratio. After that, at the high frequency, the circuit will be in unstable condition. That time a beta less than 0 if it is minus 180 degree, it is greater than A if it is unstable. At the low frequency, A beta greater than 0 and the closed loop gain will be less than A if in the stable condition. This is the characteristic, that is the effect of feedback in open loop gain. In the frequency compensation, it is used to obtain bandwidth equal to infinite and a low closed loop gain. Under that external frequency compensation, it is used to obtain closed loop gain with external compensating components are used in that, but it will be alter the open loop gain when doing the external frequency compensation. So under that, first one is dominant pole compensation. The uncompensated transfer function of op-amp in open loop gain condition, it is given as equation number 1. And dominant pole connection, so the rough connection is taken here for an analysis. Here it is called dominant pole frequency, ft equal to 1 divided by 2 pi RC. This is the compensated transfer function. So by doing the analysis, finally we are getting the A dash, that is equal to A into 1 divided by 1 plus J into F by Fd, equation number 2. And equation number 1 will be write it as equation number 3, and from that equation number 4 with the 3 corner frequencies with the dominant pole frequency Ft. This is the characteristics of frequency compensation. So this area is called a dominant pole compensation. So advantages: high noise immunity, noise frequency components outside bandwidth are eliminated. Disadvantages: reduces the open loop bandwidth. And pole zero compensation, we are taking this rough diagram for an analysis. It is an amplifier circuit. So this simple basic approximation is listed here. So by doing the analysis, we are getting A1 value. So after that, followed that by doing some mathematical simplification, we are getting equation number 5. So this is the comparison diagram of by using with the F1, F2 and F3 corner frequencies. Next one is internally compensated op-amp or compensated op-amp. Many op-amp have internal connections to allow the external compensating network. Op-amp with built lag compensation, which is performed by making the use of Miller effect to generate large capacitance. Some applications, broad bandwidth of uncompensated op-amp is not needed. Example, instrumentation circuits. The op-amp is required to amplify the slow changing signal. Hence, it does not need high frequency responses. They are stable and without externally connected compensating components. Next one is slew rate. The output is output takes to change from 10% to 9% of that final value, that is called slew rate. For that one is example as voltage follower. The maximum frequency in hertz, that is equal to slew rate divided by 6.28 into Bm, maximum voltage. Slew rate can also be defined as dV0, differential output voltage divided by with respect to time. Under maximum condition, that is equal to omega Vm into the unit is volt per second. Mainly slew rate occurred because of capacitor at high frequencies, RC pairs in cascade connection, and finally because of that it leads to sawtooth waveform. So this is the graph for different frequencies.